For our final percent question, I have what I called a combined percent question, not just because it is testing all of our percent translation skills that we have been working on up until this point, but also because it combines the topic of percents with other quant concepts. And that is really how you're going to see most quant questions. They don't fit neatly into just a single category. Most questions, especially hard questions, they are going to test multiple concepts. And that is how you really want to start seeing most of your quant questions. You want to see how everything is related, how everything overlaps, because that is really when you sort of become like Neo in the Matrix, where you start seeing all of the connections, you start seeing the common threads, and you are able to anticipate then where questions are going before you even finish reading them. And when that is the case, you instead of thinking about questions as being, oh, this is a percent question, you start just thinking of your percent knowledge as being a tool. It is a tool to answer any type of GMAT question. And so let's use our percent knowledge as just one set of tools for answering this question here. If x, y, and z are positive integers such that increasing x percent of y by y percent equals z, is z an integer? So we need to translate our prompt here. We want to extract as much information as we can from our prompt before looking at our statements. So it's asking us about z, and we know z is equal to something. So what is z equal to? So first we have x percent of y. So let's translate that. So that means x over 100. So that's x percent of y, which means times y. And then it says we increase this by y percent. And so that means we take this and we multiply it by 1 plus y over 100. So these are all translations we have made before. So go back if you don't understand where we came up with this. And so now z is equal to, so this is just xy over 100. And so if I want to simplify this as much as I can, maybe try and get this over just a single denominator. So this term here should be 100 over 100 plus y over 100. So this should give me z is equal to xy over 100 times 100 plus y over 100. So now I can get this all over a single denominator of 100 times 100, which is just 10,000. So z is equal to, maybe I won't multiply all of this out, so this is just xy times 100 plus y over 10,000. And remember, so I'm rephrasing my question here really. I want to know, is z an integer? So z is equal to this, and I want to know, is this an integer? So when will this be true? So in order for z to be an integer, and remember x, y, and z, they can't be equal to 0. They all have to be positive integers. So we don't got to worry about that option. So this means our numerator here must be a multiple of 10,000, because for z to be an integer, our numerator has to contain a 10,000, so it will cancel out our denominator. And so maybe I wouldn't actually write my question like this. I would just sort of keep it in the back of my mind. You can really think of our question though as being, is my numerator here a multiple of 10,000? Does it contain a 10,000? Now, how we get there doesn't matter. So for example, if I know x is a multiple of 10,000, that would mean this whole term here, xy, is a multiple of 10,000. And so 10,000 times whatever this is, will also be a multiple of 10,000. And so in other words, in that case, my entire 10,000 came from my x, but it doesn't have to be that case where the entire 10,000 just comes from a single place, for example. So if I know this xy here is a multiple of 100, and then 100 plus y is also a multiple of 100, well then together I would know when I multiply those two things, I get a multiple of 10,000. So I don't care how I get my 10,000. I just want to know between these two terms in my numerator is do I have a 10,000? So statement 1. So statement 1 says x is a multiple of 10,000. So this is also something that is true. On a lot of data sufficiency questions, they give you 3 variables, x, y, and z. And if they're asking you about z, well, it probably really means you need to know something about x and y. So here we know x is a multiple of 100. So we're looking for a 10,000 in our numerator. We know we're going to have a 100 from this term here. So xy will contain a 100, and that is all from our x. But if x contains a 100, this whole term here, xy, must be a multiple of 100. And so now our question becomes really, do we have another 100 in this term here, our 100 plus y? But because we don't know anything about y, we can't say. So for example, y could be equal to 200, and then 100 plus 200 would be equal to 300. And in that case, we would get our other 100, and so we would have a multiple of 10,000 up here. But y could also be equal to 1, for example. And so y is equal to 1. 100 plus 1 is 101, which is not a multiple of 100. So this is going to be insufficient because I don't know anything about y. Statement 2. So now, before you start saying, so statement 2 will be insufficient too, because in statement 1, I didn't know anything about y, and that was insufficient. Here, I don't know anything about x. But before you make that assumption, let's see if it is in fact true. So here I know y is a multiple of 100. So that means in this term here, my xy, I have a 100. So now it's not coming from the x now it's coming from my y, but still that means this entire term here, x times y, must be a multiple of 100. And so the question once again becomes, do I have another 100 in this term here? Because that is what I need to make a 10,000. And so I am adding, so I have 100 plus y. So 100 plus another multiple of 100. And so if you start testing examples, y could be equal to 100, y could be equal to 200, y could be equal to 300. You should see that no matter what, you are always going to get a multiple of 100 here. And in fact, there is a rule. And if you don't know the rule already, you certainly will once you go through the primes and divisibility section, which I highly recommend. Anytime you add two multiples of a number together, the sum is always going to be another multiple of that number. And so if you add 100 plus another multiple of 100, you will always get a sum that is a multiple of 100. So 100 plus 200 is 300, which is another multiple of 100. 100 plus 300 is 400, which is another multiple of 100. Or if you add something like 12 plus 24. So these are both multiples of 6, for example, and they give you an answer of 36, which is another multiple of 6. And so statement 2 is actually telling us we not only have 100 here, but we're also going to have another 100 from this term here, which means between our two terms in our numerator, we are going to have a 10,000. Because we're going to have 100 here times another 100 here, and 100 times 100 is 10,000. And so even though we don't know anything about x, we only need to know something about y in this case. And so B actually is sufficient. And C would be the trap answer choice, because it's obvious that if you know x and y are both multiples of 100, well, x times y, that means it contains 100 times 100, which is 10,000. And so that will definitely cancel out our 10,000 here. But what is less obvious, and what you need to think about a bit, is that statement 2 is actually sufficient on its own. So B is the answer. This is a very good question. It's a good question to, even if you understand it, to go through it again slowly so that you can do it step by step, because there's a lot of stuff that you can learn here, not just about percents, but about divisibility, about data sufficiency in general. So I would star this question.